Tonight, we're going to be doing an update on photonic propulsion minus the EM drive stuff at the beginning of it. But first, as usual, we'll do the news. So the James Webb Space Telescope is on track to be launched on December 22nd. That's a move out from the 18th to the 22nd. It's going to be launched by Ariane rocket. So we'll actually do our discussion next week on the 18th, and then on the 11th, and then on the 18th, we'll probably just do a short status update kind of thing. Next week, when we do our web event, we'll also not have a news segment at the beginning because we want to get our subject matter expert in, get our presentation done, and then let him go. We don't want to have him sit around for an hour while we jaw about news. He's a busy guy. So there's an Atlas V rocket that is going to be launching military space stuff, satellites and things. And that's coming up soon. It's now set for 4:04 a.m. It says delayed to Monday, but I think that was earlier today, which now it's delayed to December 6th. It was supposed to be earlier today. And that's by the United Launch Alliance. This is one of their remaining rockets. I don't know how many people heard it this week, but Blue Origin announced yet another delay in having their BE-4 rocket engines available for the Space Launch System to use to replace the Russian rocket engines that the US Congress said you can't use those anymore because we'd rather build our own. So anyway, there's lots of rocket launches that have occurred this week and will occur in the coming week. There have been more delays by Boeing in resolving the glitches in their Starliner crewed capsule. They're supposed to go to the International Space Station. And because of those delays, NASA is awarding 3 more Crew Dragon flights to the International Space Station to SpaceX. They're basically taking them away from Boeing and giving them to SpaceX, which I'm sure doesn't go over well with Boeing. But if you've got things you're not fixing and you can't successfully launch an uncrewed capsule to the ISS autonomously, and until you're successful at that, they won't let you launch people on board, then you're number 2 and trying harder. So in the interim, they will take the things that Boeing used to have as committed launch contracts because NASA and ISS needs to get the job done, and they'll transfer those over to SpaceX. More revenue for the SpaceX coffers that was not expected. So the dire straits of maybe going bankrupt that Elon was warning about for SpaceX may not happen. They may find the cash they need. And I found this one a great way to work around a problem. People might be aware that the SpaceX Starship rockets, the literally largest rocket humans have ever built, was to be launched from Boca Chica, Texas. And they were waiting on the FAA to give them final approval to schedule out launches that might occur once or twice a month for the next few years. And that scared the bejesus out of all the locals at Boca Chica, Texas, between people being concerned that the road would be closed and they couldn't get to the beach to go to the beach for enjoyment, or it might harm the local wildlife, even though they've already launched several things and exploded several things. And the environmentalists said it didn't really harm anything because where the stuff blew up was already on areas that were cement covered. So not really an ecological problem, but they still wanted 2 and then 3 environmental reviews of what SpaceX was doing for the Starship at Boca Chica. And I just looked at that and said, who's paying who money underneath the table to make sure that SpaceX isn't successful? So what SpaceX said was, no problem. We have enough cash in the bank. We will build another Starship launch complex, this time at Cape Kennedy in Florida, which is already well known to have an environmental area that survived very nicely through multiple Saturn V launches and multiple rocket explosions. So you want to stop us at Boca Chica? No problem. We'll just go build a Starship launch complex in Florida, where there's already launches taking place. I just think that's just the Elon way of doing things. You want to get in my way, you want to stop me from achieving something, I'll just make you irrelevant. So that was just an interesting tidbit of news to come out this week. And I don't have an article on it, but the same thing occurred with the Tesla Gigafactory in Germany. The local government is now complaining that the factory is going to be doing more things than they originally thought it was going to be doing, and it's going to be cranking out more cars per month than they thought it was going to be doing, and they want to go back and reanalyze things again. But it turns out that there's a way to get around that, which is have the Tesla auto workers in Germany join the German National Union. And in Germany, as part of the EU, unions are handled differently. They're not a private business. They're a collective government relationship. So they're more pro getting companies advanced, getting the employees educated. And so in order to get the additional credit on cars built in the US by union employees, Tesla's looking at its employees in the US joining the German auto union, which that's just so, end run around it. It's like, okay, you won't give us full credit on selling cars made in the USA because we're not using United Auto Workers union employees like GM who would get the full credit. No problem. We will have our employees join a well-recognized international union, German-based. So it's just another example of, you want to get in my way, you want to cause me grief, you want to stop me from doing what I need to do, I'll make you irrelevant. So it's just his way of doing things. And for those that weren't watching it, there was another rocket launch. This was an Arianespace Soyuz rocket launch, and they're launching 2 European Galileo navigational satellites. This is kind of like the EU's version of our GPS system, but for the EU, not for the US. So they launched that. Another rocket that went up. And then another rocket that went up this week was SpaceX launched another Falcon 9. I think it was on its 9th reused launch, that boost, that first stage. And they launched, I think, 50 some odd Starlink satellites and 2 private satellites. And I think the revenue they made off the 2 private satellites, plus reusing the existing booster, covered the cost of the Starlink satellite launch, which is, that's the way to do business.
Yeah.
Real ride sharing. And in the celestial world, there was a solar eclipse that took place that you could only see from Antarctica. And somebody wondered if the penguins would look up and see it and hurt their eyes. No, because the penguins aren't wearing solar eclipse sunglasses.
So does it hurt their eyes?
It was something people asked, but nobody stopped to evaluate the penguins after the fact.
Ah.
Well, if it did, there's not much to bump into except other penguins, so they're probably okay.
And I look at it as, if you ever heard of snow blindness, this is because snow is so white and reflective that it'll actually be much brighter than anything you would normally see. So if you've been out snow skiing and you did not wear darkened goggles, when you come into the lodge afterwards, everything is really dark because your pupils have so closed down that, to protect you from the snow blindness, that when you go indoors into someplace dark, it takes a while for your pupils to open up again.
Mm.
So penguins are always living on snow and ice, which is very reflective. So I don't think it would have bothered them, but that's just me. And also they're in Antarctica where the ozone hole occasionally shows up and allows more UV light down onto the Arctic ice than would normally be seen at higher latitudes, which penguins don't seem to go blind from that. So I'm going to say, until we find otherwise, I think they were just fine.
Well, that's good.
Yeah, good for the penguins. I'm happy.
Yes.
Yeah,
Yes.
but they have a hell of a time when they go into the lodge.
Yeah, they don't even go into a cave or anything. When there's a horrible winter storm in Antarctica, they just all huddle around into a clump of penguins, and they have patterns that the penguins will shift around from the outer edge to the inner core and then back to the outer edge again. So no penguin has to stay out in the wind too long.
That's nice.
Just a behavior. Yeah, they've got videos on the internet of penguins shuffling around from outside to inside to outside.
Are there many caves up there? I mean, why don't they go into a cave? I mean, that's nice that they shuffle around, but who wants to be out there in the cold at all?
Well, the glaciers go all the way to the edge of the ocean, to the Antarctic Ocean. So there's no caves near the shoreline. So there, aside from ice mounds and things like that, there is no refuge from the wind and the ice and the low temperatures for the penguins. And when the icy weather lets up, this is weird. In order to increase their body temperature, they'll actually go in the water, because there's a difference between the air temperature and the water temperature. So they'll go into the water. Their feathers are very oily, so they don't get soaking wet. So they'll go in, warm up, and then pop out and come back on shore. So they've got a whole thing going, and they've been doing that for a long time. So I guess they've got it down to a good pattern.
Well, that's good. Then it makes sense that they do that. I'm just thinking if there's a nearby cave, why wouldn't you just duck in? But that makes sense if they don't have the availability.
Right, because the glaciers, are probably many, many miles from the shoreline. It's just ice all the way to the water's edge. So there's no place where a cave could exist. Now, a cave might be a mile deep under the ice, but until the glacier goes away, which maybe will happen in the next decade, you can't get to those caves. And the caves that are inland are, maybe hundreds of miles inland, and the penguins aren't going to go that far.
Yeah.
Okay, that's all I had in the news. Did anybody see anything else that I didn't notice?
Comet Leonard. Have you noticed that?
Comet Leonard?
Yes, there's a new comet recently discovered, and it should soon be visible, possibly to the naked eye. Right now, they're saying it's near, was it Arcturus? I forgot which. It's near M3.
Okay, Leonard as in Leonard?
Yeah, Leonard.
Is it named after Nimoy?
No.
Okay.
I wish.
Yeah. Okay, I'll have to look it up. A lot of times when the media promotes these as, it'll soon be naked eye visible. And then I'll actually go do the simulation in Starry Night and find out it's going to be magnitude 11. That's not naked eye visible.
I was looking on space.com, and they, of course, caution that comets can do unpredictable things, and you never know, but maybe.
Okay. I'll take it with a grain of salt, and I'll do the research on it and look it up. But we won't catch it next week, because next week we'll talk about the Webb Space Telescope. I may put out, if I find it's really visible, I may put out a special news email for it.
They're saying right now it's in the very early morning sky, and in a couple of weeks it'll be in the late, let's see. Yeah, early morning, evening. And then it'll be early evening.
Yes, early evening. Yeah, it'll be early evening, low in the western sky. Yeah.
Yes.
Yep, I've seen several comments that way in that direction that required my 7-inch Max-Utov Cassegrain telescope to even see it.
Yeah.
But if you know where it's going to be and you load that up into your hand paddle, you can make the telescope go to it. But first, what you do is you make the telescope go to a known star You get it lined up on that. You adjust the mount to be precisely on that, and then you tell it to go to the comet, and then you can see the comet. Or if you get
Yeah.
real lucky and know exactly where to look, you can sometimes see them with good binoculars.
Yes.
Speaking of things you might see in the night sky, there is a prediction that there will be a nova in Cygnus near one of the wings, near the center of one of the wings of Cygnus the Swan, within the next year. Maybe sometime
Wow.
mid to late 2022, there'll be a nova. This is a what they call a red nova. If you have two stars that are of roughly the same mass, but they're close enough together that one has a little bit of edge over the other one, they'll actually come close enough together that they'll draw upon each other's plasma, and whichever one's slightly bigger will suck away plasma from the slightly smaller one and accrete it onto the surface until it can take no more, and then it will explode. That's a classical nova. And when it does that, it takes out both stars. So they're looking at it as it could be an event that occurs initially in radio, and then as a gravitational wave, and then in UV and X-ray, and then visible. But when it becomes visible, they expect it to be visible for a month. And you know, they're giving it the usual, it'll be visible in the daytime, maybe. So
That's
it'll be,
exciting.
yeah. I forget the number. It was found by the Kuiper program. So it's KIC, K-I-C 8792222 or something like that. If you just say Red Nova 2022, you can probably find it. In fact, why don't I just do that? Let's see if I can do that now. I'll go ask the great googly oogly. Red Nova Star 2022. And there it is. Well, it's in Forbes of all places. That's an artist rendering, obviously. I know that's a picture, but that's fabricated. That's actually a nova. They're showing a bunch of old articles. I actually want the information on this nova. Okay. How about Discover magazine? Oh, wait a minute. Two stars won't collide into a red nova in 2022 after all.
Oh,
Oh, that's the one.
Yeah, well, it says we're disappointed too. Oh, that's weird because it says September 7th, 2018. They did predict this back in 2018, and then they said, we think it'll happen in 2022 because they originally predicted it for 2018. And now it says maybe it won't happen in 2022 after all. And I've got only one article left before I have to actually pay for Discover magazine. But if I just do a select of that, it's just 1,800 light years away in Cygnus the Swan. So now if I search on the actual name of it, yep, there's a Wikipedia article. It was predicted to result in a merger in 2022, plus or minus 0.6 years. Now they're saying maybe not. If it does go, you heard it here first.
did it say why not?
Well, however, a reanalysis of the data in the September 2018 revealed that the prediction had been based on wrongly timed observation negating the predicted merger. But they were saying that they were close enough together to have started to exchange plasma. Once you're that close, you're not going to separate apart again. It's just a matter of how soon you're going to smack into each other. But it is unlikely that the system will end in a merger at the predicted time. But the cause for the period variation is still unknown. The original data from 2018 that predicted it in 2022 doesn't seem to be accurate. However, they still think that it might occur. KIC 9832227 in Cygnus the Swan.
Well, mergers are always controlled by lawyers.
Yeah, or Congress.
Yeah.
But that's in the constellation Cygnus the Swan. That's the same constellation you find Deneb and Albireo. So if you're familiar with those two stars, then it's going to be in the same neighborhood. So when it goes, you know where to look in the sky. And let's see, upcoming stuff. So I posted last week's presentation on use of a pan-tilt zoom surveillance camera for astronomy, an update. posted that on the BA YouTube site. Next week, we'll have our James Webb Space Telescope session with Dr. Will. The launch of the Webb is moved out to December 22nd. You can start watching it live at 7:15 a.m. Eastern Time. It'll actually launch at 7:20, no earlier than 7:20 a.m. It might be a little delayed for weather, but that's when it's expected to go up. There will be no online session December 25th and January 1st. Remember last week I said that starting in the new year, I don't have any topics for the first 2 weeks. And lo and behold, I was looking at things and found a topic: the business of androids. This is very interesting because there was an android in the news this week. It was one of those spooky looking ones. So this android is fully moved, and the mouth moves, and it makes a speaker in its chest. Like, how can you get so much right and get that one thing wrong? The voice has got to come out of the mouth. Yeah. But you can see this was 6 months ago. They had this robot and they were showing it off, and it was just too garish for the general public. So they went a little further along and they made it look more human-like, but they didn't completely cover the body with skin. They only covered the hands and the front part of the head and the ears. But when you look at it, it's kind of like a boundary condition. If you haven't got it fully right, don't make it look too human. If you've got it fully right and it really looks and behaves as flowingly, seamlessly, and not herky-jerky, then you need to make it look more like a human. So the presentation in early January will get into all those nuances of how to make the movie I, Robot come closer to reality.
Well, they could put some clothes on him.
Well, there's that too, but I even get into things like, what do you call them? Well, you shouldn't call it or machine or robot. You should treat it kind of like people, because there's going to be lots of these things. So you should give it a first name and a last name. Well, can you tell if this is male or female? No, they deliberately made it androgynous so that you wouldn't make assumptions about it being what can a male do or what can a female do. It was just, it can do things. And in that note, they would think about giving it a name like Ryan, which is androgynous. Is it Ryan the boy or Ryan the girl? You could just call it Ryan. Now, what would you give it as a last name? Well, you would want to pick a last name to match whatever company provided it, but you don't want to use the company name. You want to use it kind of like a product family name. So if it's a family name, it should be kind of like a last name. But then when you describe a family name coming out of a certain region, like I come from the Patillos from Atlanta, Georgia, or the Patillos of Atlanta, Georgia. So if that's the case, then you would name it, Ryan Smith of SpaceX. And that way, when you wanted to command it to do things, you would just refer to it as Ryan. And because you were looking at it and the camera saw you looking at it, it would know it was being tasked.
I just call him X23. It's easier.
But there could be millions of these things.
All right, X24, X25.
X2178594.
Yeah.
That's a good name.
Yeah. And then what if you were a warehouse and you had 50 of these? They're going to have numbers across their chest?
You can't. Why couldn't you have two with the same name? Not in the same facility, maybe, but it could be one X23 in California and another X23 in Florida. And
that does make sense because there are Smiths everywhere.
Indeed.
There are John Smiths everywhere.
Yes.
So, yeah, it's just things like that they have to figure out as far as the business goes. And do you sell companies the robots? Then you sell a service contract with them? Do you lease them out? Do you put them on a long-term lease, a lease to buy? What's the business of androids? That's what we'll get into. is the business of androids.
Well, following the current trend, nobody will be allowed to own them. Or
Yeah.
if you buy them and they break, you have to send them back to the manufacturer for repair because they won't make the parts available to the general
Oh,
public.
no. We have a right to repair our robots.
Not yet.
But I think it's now on the verge of getting to look too human. And if you just go on YouTube and you look for the words Boston Dynamics, you will find some amazing robots that they're creating for specific purposes, like moving boxes around in a factory. And those don't have to look like human beings. In fact, they can be quicker and more maneuverable than human beings, because to a factory, time is money.
You mean I could get a robot to help me pack?
Not today, no. Not yet. I know. By the time you need one, you won't be able to afford it, and you won't need one. But I can see the way that they get these down to the least common denominator in price for service rendered or hourly service rendered is to basically treat them like outsourced contract employees. So if you need one for a certain period of time every day, you might contract to a group that would give you, 4 or 5 of these things to act as your manual labor staff for your business. Just depends upon how smart you make them. If you make them too smart, they'll want their own freedom.
And their own office.
No, they're Linux based.
They'll join the German Union.
Yes, but they're being created all over the world. And different countries have a different take on how human they should look. In Japan, they purposefully make them shorter than the average height of a person so that you can have a relationship where when you're tasking them, you're always looking down to them. You don't have to look up to them. Just social customs. So I was suggesting, find out what the average height is to a human being in whatever country you're selling them in, and make it about 4 inches shorter than that, so that they don't look overpowering or fearful of them or whatever. And then I watched this video where they were showing a somewhat human-looking android that was doing Olympic acrobatic maneuvers. It was literally throwing itself into the air about 20 feet and doing multiple somersaults and landing, sticking the landing every time. Yeah. So when are these things going to be in the Olympics? Anyway, we'll get to that in January. And tonight's presentation is an update. A couple of weeks ago, we did a presentation on photonic propulsion, but as a differentiation from the much touted EM drive, as this is a more effective, more optimal form of reflective propulsion. And there were some questions that came up. People were asking, well, what about this? And what about that? And, why isn't this a problem? And so I said, let me go look into that. And I looked into it. And so we have an update. And I marked the pages that were updated. Previously, we discussed the EM drive and how photonic propulsion uses specific materials and components to make it a better solution for high specific impulse propulsion for long-duration satellites and deep space vehicles. There were comments that came during that presentation, such as the vector angle for the transfer of momentum is 90 degrees to the surface of the reflector. Therefore, in a cone-shaped reflector, it won't make it go that way. It'll make you want to go that way. So how do you fix that problem? And that's true if there was no mitigation to counter for that. So I came up with a mitigation, and you'll see that it didn't come directly, it came indirectly by way of something else, so it's proven physics. So there'll be mitigated material that counters that problem. So I've updated the content to focus on what that solution would be. And if there's any other comments, we can take those into account and maybe work it in a future update. So this is one of the original slides, and basically we've always built rockets that If you want to go up, you throw things out the back. And the things you throw out the back are chemical processes. It's either solid fuel rockets burning, solid fuel to make energetic stuff go out the back, or it's liquid fuel. We mix fuels together or ignite fuels and it pushes stuff out the back and you go up, and all of that works really great, except that you run out of fuel rather quickly. So you better be going as fast as you need to go before you run out of fuel. Oddly enough, even the biggest of rockets only go about 5 minutes or so at maximum before they exhaust all that fuel in that big rocket to launch something small into space. So that's the hurdle that you have to get past. And if you want to send something out into deep space and you want it to last for more than 5 or 10 years, you need something other than this liquid chemistry-based fuel, F equals ma, throw it out the back kind of stuff. And so they started looking at ion propulsion. And when they looked at that, it worked really well up to about 10 years. And then ion propulsion runs out of the krypton or xenon gas in a fixed size spherical pressured cylinder sphere that holds the fuel. When you're out of fuel, your mission's over. But if you're something like Voyager 1 and Voyager 2, and your electricity is provided by way of radioisotope thermoelectric generator, is basically the heat of plutonium. It's not fission or fusion, it's just thermal radiation, which goes into thermocouples, which the heat produces electricity, and that's what powers the spacecraft. And it'll do that for a number of decades, and then it slowly declines. Well, if you've got that for your source of electrical propulsion, for your radio and your sensors, and you're just on a winging it transition, velocity on a trajectory going out of the solar system, you can have things like Voyager 1 and Voyager 2 that are around 50 years moving through space. That's the kind of thing you want. So anything that has lasted many decades has always been of this kind of defined trajectory where it's just moving on its own. There's no actual propulsion needed, which is not entirely true. There are solar wind adjustments they have to compensate for, which means they occasionally have to use their inertial mass or gyroscope to rotate themselves so that their antenna could continue to point towards Earth. And so the fixed fuel capacity is really the limiting measure. Now, this is unrelated to faster than light travel. If you want to go faster than light, you need a totally different kind of propulsion. This is really for when chemistry runs up against the fixed fuel tank, then what do you do in order to go even faster and for a longer period? So that's where photonic propulsion comes in. They found out that ion propulsion, which doesn't put out very much force, the old saying is the weight of a sheet of paper, letter-sized paper being lifted by your hand, is about the amount of force that an ion propulsion system puts out. That should say 19 millinewtons or 19 thousandths of a newton. They've tried different chemistries along the lines of ion propulsion. For example, the NASA InStar engines use xenon, whereas the SpaceX Starlink ion engines uses krypton. And there are new NASA test propulsion systems that use iodine, because iodine or iodine, iodine, they can package up as a chemistry and make it a solid. And if it's a solid, it doesn't need to be refrigerated or put under pressure. And then they use a laser to melt the iodine to make it a gas, and then they can ionize the iodine gas to use as their propulsion source. But true photonic propulsion is not even that, because that's just a fancy form of ion propulsion. So back when they discovered in the 1800s that sunlight reflecting off of stuff transfers momentum to stuff, they had as their light source the sun. And they had as their mirrors polished metal. So if you give that chunk of metal a really good rub and you shape it, then you can get a good reflector off of it. ignoring the fact that it's probably only about 70% reflective because it's got microscopic pits all over it, and you're shining it up. You can see yourself in it, but it only transmits a very narrow wavelength. In the early 1900s, they worked a little bit better. Instead of having sunlight, they had an arc lamp. And instead of having polished metal mirrors, they had silvered mirrors. Now, these are the early mirrors, very similar to the kind of mirror you look at your face in, those kind of mirrors. What they didn't have access to was even higher power in light sources and very precisely reflective surfaces. In the 1930s, they moved up from arc lamps to tungsten filament electric bulbs, which was great for the 1930s, but compared to today's high output LEDs, as the saying goes, they can't hold a candle to them. And these days we have sputtered electrically coated mirrors that are around 99.9% reflective. It wasn't until 1937 that they had dielectrically coated mirrors, and it wasn't until 2010, not that long ago, that we had these really high output LEDs where they took a bunch of LED chips and all made them produce the same color light. And it wasn't until 2014 that they realized if they changed the chemistry of the individual LED chips, they could get even more light out of them. And it wasn't until 2016 that they found that they could push this even closer to higher energy output, nearer to ultraviolet LEDs. And that was courtesy of Blu-ray devices. They wanted to make cheaper and cheaper Blu-ray devices, and Blu-ray devices needed blue lasers. But blue lasers are more expensive and optically more complicated to set up. So they said, how do we make blue LEDs really, really bright and really, really deep blue? So they came up with this manufacturing process in 2016 to make what they call royal blue LEDs. They're very high output and they're very nearly UV, but not quite. So how do you maximize it? Well, a shorter wavelength will transfer more momentum. The more photons you can pack per square millimeter, the more transfer of momentum. The more reflective your surface is, the more you transfer. The angle of reflection needs to be oblique, shallow, small number of degrees, sort of a pointy cone kind of thing. And you don't want any of the photons to be reflecting at 90 degrees because then they essentially transfer to heat, and you have problems with the heat being countered to the direction you want to travel. And you need to phase align the photons. So instead of just turning the beam on, you need to turn the beam on and off, on and off, on and off, very, very short periods of time to get all the photons kind of smacking at the same time, as opposed to randomly. So that's what we're talking about is photonic propulsion. It's basically optimizing this reflection. And if you think about it for a moment, if you have an emitter and a reflector, and you don't have any tank full of some kind of fluid or helium or any of those fuels, that's lighter weight. If you don't have any plumbing lines or valves or fuel pumps or combustion chambers or exhaust nodules, it's lighter weight, it's lower mass, it's physically smaller. That's a dramatic reduction in the spacecraft parts count, complexity, reliability. It's just all better. Think of it like if you were to take apart an internal combustion vehicle and you were to take apart an electric vehicle, the internal combustion vehicle would have more parts in it. And you'd think that more parts would make it heavier. But then if you look at the electric vehicle, the batteries collectively make up more weight than does all the parts you don't need anymore. So it's a compromise of one versus the other. But the other thing you can think about is if you get a photonic thruster as a means of propelling things, then you can get rid of all of those massive spinning wheels for adjusting your angle and just use more of the thrusters. There's no fuel you're going to run out of if you have solar cells or an RTG producing the electricity. Most people don't consider this, but if you start looking into these spinning wheels, the gyros, the reaction wheels, the inertial mass rotation mechanisms. Once you start rotating in the direction that the wheel is moving, the wheel can only go so fast. And if you're already rotating at that speed, you cannot go any faster to rotate yourself around. You have to literally reverse the motor on it to slow it down so you can make it go faster again. This is something called spin-up overload. And it's not discussed much, but when I was doing the research on the James Webb Space Telescope, it has these mass wheels that it can use for rotating the spacecraft to make it line up on things. And when it comes into a spin-up overload issue, it has to shut down all of the instruments and then spin the spacecraft in the opposite direction to regain the momentum in the wheel. And then they realign it with thrusters to where they want it to be. And now they can use the momentum wheel again for the fine positioning. Plus, if you've ever looked at a spacecraft like the Lunar Excursion Module, the LEM, it has all these little thruster nozzles all over the body of it. And there's clusters of them. There's 3 in each basic quadrant of the spacecraft. And those are reaction control thrusters. And that's because how else are you going to rotate it in all these, pitch, roll, yaw, 3 axis of each directions? Well, those are only about those used to be only about 1 Newton of force. So if you can get something that would give you even 1/10 of a Newton, you just leave it on longer. And now you have a solution for it. And the other thing is, I saw this with the Webb Space Telescope. When you fire up your chemistry-based propulsion system, it actually spews junk, garbage out the nozzle. That's the stuff that it's accelerating, and it's chemical. And those chemicals can wind up being a residue on your instruments, because when you spew it out, it's charged particles, and it has nowhere else to go. So it goes, oh, look, I find something that's the opposite charge, the spacecraft I just came from. So when you spew out that cloud of whatever, if you're not going too fast away from it, it turns right back around and comes and sticks on the outside of your spacecraft, which can contaminate your sensory instruments. So if you look at the Webb, the telescope is on one side of it, and the thruster is on the bottom side of it. And the reason for that is they don't want the thrusters exhaust contaminating the instruments on the top of the telescope where the imaging is done. So they only have them down there, and they use the reaction wheels to rotate the telescope in those directions. Okay, so what photonic propulsion is not? People were getting confused as to, is this anything like that ion engine or the Vassimer engine or nuclear propulsion or solar sails or warp drives or impulse drives? It's not really like any of those. It's truly photons reflecting off of something, transferring momentum to that something. And this is the basic engine design. You've got a heat sink that dissipates the heat off the light emitter, and then the light comes out one end and reflects inside of this cone shape, which has a hole on the end of it. And then as soon as the light reflections get almost to 90 degrees, they get exhausted. And the direction of travel is to the right, which is opposite to what you would normally do. Normally, you'd throw things out the back and go to the other direction. In this case, you're throwing photons that you no longer need out the front, and that's the direction you're going, because the photons are being reflected off the cone, and it's transferring momentum to it. But that's when Helen pointed out that, well, the way that the reactive force works is when you reflect off of something, the momentum is transferred at 90 degrees. So if you have a mirror that's like that, which would actually be in a cone shape like that, and the light comes through at 90 degrees to it, then it's not going to push the mirror this way, it's going to push the mirror this way. And if that's your cone, then it literally wants to push the cone apart. So you need a solution to that problem. And the solution to that problem comes from fiber optic cable. So when they first started making fiber optic cable, they said, why don't we run a fiber optic cable across the floor of the Atlantic Ocean? And now we can connect things up at high speed from North America to Europe or to Africa. And they tried that and they found out, the light only goes so far. Now they didn't actually lay the cable into the ocean. They actually tested the cable out on the shore in big reels, and they found out the light doesn't go as far as we thought it would. And it's because when the light reflects inside the cable, if the light reflects such that it comes at 90 degrees, then the light literally goes into the reflector, gets transferred into infrared heat, and no longer bounces anymore. It won't make it to the far end of the fiber optic cable. So they found that if you make the fiber optic cable multiple layers, and you have an inner layer that is pretty much transparent, except it's of a glass chemistry that will bend the light towards ultraviolet. So it'll literally, if you think you're coming into the outer shell of the cable 90 degrees, it'll actually bend the light so it sort of gets down the length of the cable and not cross to it. So that's pretty much transparent. And then on the outside of that layer, you have a cladding, and that cladding is 100% reflective, highly reflective. So anything that wants to come in at 90 degrees actually gets bent shallower than that and then encounters the reflector and will now bounce back into the cable. So instead of it bouncing around inside the cable, it actually bounces to the outer edge of the cable and then back in. And that confines the beam of photons more towards the core of the fiber optic cable, and that made the light go much farther. Well, we do the same thing. We start out with fiber optic cable that's just a cylinder. We start out with our propulsion reflector, which is just a cone. And then in order to improve it, they actually made it a cladding. And so they have two layers. And we would do the same thing with our cone. We'd have an inner transparent layer that has a chemistry such that the index of refraction bends the light inward. And then we'd have a reflective surface on the outside of it, which pushed the photons back in. So that's the solution to the problem that Helen so rightfully pointed out when we had the last presentation on this. So how to calculate the net effect? How much force are we going to get out of this? I had to add a section in here on how you calculate that vector angle so that it gets the light back in without having it go 90 degrees to you. Therefore, instead of pushing the cone this way, it's going to push the cone that way. And the other thing that I discovered, and this was from a different presentation that I did, is that if you get too close to ultraviolet, your reflectivity goes down because ultraviolet does not like to transfer through glass. It gets blocked by glass. So you have to come up with exotic materials for your reflection. And so by not making the emitter in ultraviolet, making it just shy of ultraviolet, using those lovely royal blue emitters, you can get 2 times the momentum transfer that you would for microwave without getting into complex reflectors that you would need for ultraviolet. So you don't want to take the wavelength too far. You want it close to, but not quite UV, because when you get into UV, X-ray, and gamma, how you make things control the flux, the density of photons, just gets very exotic and expensive and heavy physically, because when you get into X-rays and gamma rays, you need shielding, thick shielding, and that just makes your spacecraft heavy. So just don't go that far. So don't take the wavelength too far. And we found out last time that if you want to, you can get up to a very high output LED, but if you do it at broad spectrum, you don't know what the actual maximum wavelength out is going to be. You don't know if it's going to be blue or red or orange. It just looks white. So what you want to do is have a monochromatic ray, single wavelength coming out where all the energy comes out at a known wavelength. And then it can take the power too far. I know that you can actually buy these LED emitters up to 100+% watts of output very cheaply. Literally, you can, for probably under $100, buy yourself a 100-watt LED. They use them in grow houses. I wouldn't know anything about that. But it's much better to get yourself a lot more 3 or 5 watt LEDs. And the idea is that LEDs have this thing called efficiency. It's how many watts you put in versus how many watts of light you get out. And as you make them higher and higher wattage, even if the percentage is the same, the inefficiency of total watts wasted goes up. So don't go too high. 3 or 5 watts per propulsive source is good. And if you need more, cluster them, make a few of them. It's good for redundancy. And I updated the index angle based upon having to change the material to make it bend the light inward. And then I mentioned the reflectivity and how the outer cladding adjusts that. And then here's a slide discussing the transfer angle and how the change in index of refraction actually bends the light more towards the direction you want to go, and how that relates to optical fiber. And then we got into the math of how do you calculate the end result? And it goes through a couple of slides here. If I look at the nanometers of output of the LED, that tells me how much energy how much momentum I'm transferring per photon. But now I need to calculate, well, how many photons and over what square area, and add all that up, and then you'll find out what you're getting from the device. And then if you're switching it off and on really fast, maybe you're only getting 50% duty cycle. So you have to back it off a bit on that. And then, as I mentioned, the power efficiency. Well, if you pump 3 watts into a royal blue 440 nanometer LED, you may put 3 watts in, but the most watts of photons you're going to be getting out the other side is about 1.4 watts, and the rest of it is heat, which goes into that heat sink out the back. And then there's the pluses and minuses of calculating it all down and saying, well, how much would we get? Well, it turns out that an N-Star engine would like 14 millinewtons, and theoretically this should get 109 millinewtons. So this should be more force than an ion engine, but you have to prove it out. The math is maybe correct, maybe not correct. Maybe there's some factors that weren't taken into account. But this is how you optimize it. You start with the shortest wavelength you can get. You get the most photons per square millimeter that you can get out of it. And then you want it to have a very narrow angle of reflection. And then you want ultra short pulses to smack it collectively. And how much reflector you're going to need is really not, the open end needs to be not much bigger around than the actual LED itself. So tiny. And this is the end result. Is I assembled this from parts that I bought on Amazon, and you can see that it's rather leaky because I just took an off-the-shelf reflector and used it, and it definitely makes the light come out the back as well as the front. It's supposed to be just coming out the front. And now that I'm studying multiple layer reflectors, I have material for my 3D printer that I can still use this cone on the outside, but I'll make a clear cone that goes on the inside of it that bends the light through index of refraction change, bends the light more upwards so that less of it will come out the back end. And I'll make the 3D shell that goes on the inside cover the LED more completely so that less of the light gets out of it. but that's a project for another day. And lots of people will say, how do you know it works in the vacuum of space? Well, I own one of these. It's a vacuum pump and a vacuum chamber, and has a pressure gauge. And so that's how I would test it in the vacuum, but I can't tell how much force it's putting out. That's the next step is, gee, I wish that some other folks out there would actually measure how much force it's producing. Turns out NASA does have an impulse pendulum, a force meter that can measure 1/100000th of a Newton. So that would be fine if they would do it. But unfortunately, because of the EM drive, and it's so much of a laughing matter that as people come out with new forms of propulsion, if it's not tried and true chemistry of some form, it just basically gets laughed out of the ballpark. So I'm going to have to come up with my own means of measuring it that other people can reproduce, which gets us to that. How do you measure such a small force? And the way I'm going to do it is on the left there. You have a mass, the M, and you take a force and produce it in the arrow direction where that F of t is. That's the force over time. And that will rotate the spring, and therefore it will produce this much force over this angle, and you can measure that in milligrams, which I think it'll be more like nanograms, but that's what I'll have to produce is one of these force meters that will do that kind of thing. The one that NASA has actually looks like the third one, but they have a lot of money invested in it. So when they want to test it out that way, it works differently, but it calculates the same thing. But then again, people will say it's implausible, like that EM drive. But if you think that's the case, then you haven't noticed the improvements. And it literally took about 40 years before there was enough understanding of ion propulsion to actually put it as maybe this will work, as a technology demonstrator in a deep space probe called Deep Space One. And it worked so well that they didn't even touch the engines. They copied the engine design and put 3 of them on the Dawn spacecraft when it went looking for an asteroid in the asteroid belt. And they found that it worked well, so they sent it to another asteroid. And that's where it ran out of fuel, out of ion drive fuel. But what people always want is, well, how am I going to launch one of these things from the ground? Nobody seems to ask that of ion engines, but if you come up with a new form of propulsion, people will say, I'm used to like big rocket launches. How am I going to launch that? Well, yeah, you'd launch it in stages just like you do a regular chemical rocket, but the stages would be much, much smaller. And you might start out with the initial stage having a lot of emitters, and they're connected to a power source on the ground via a very thin wire. So it would have enough force to start the acceleration, and then it would run out of length of wire and it would drop away. And then you'd turn on the second layer, which might have some lightweight batteries. They would kick it up a little further, and then you'd finally get to the third stage where it would be using small solar cells to add more momentum to it. So that's how you launch one from the ground. And as I mentioned earlier, it's not the same as a Crookes radiometer or an ion or Hall effect drive or solar sails or warp drives, or the latest one is the Farron-Woodward Mach effect Casimir or Mega drive, which is touted as being similar to a Star Trek impulse drive, but not really. It's more like ion propulsion. And then conclusions. Added to the conclusions that if you want the reflector not to push sideways, if you want it to push forward, then you're going to need to have a fabricated multiple layer reflector that's transparent but has a chemistry that changes the index of refraction. And then on the back side of that is where you actually put your reflector. And then that will transfer the momentum in a more linear fashion. And I updated the hyperlinks to include optical fiber and how that works. And with that, open to questions.
Very nice.